Hi there. So in this last video, we're going to go through the final details of preparing this machine for use within ENCY itself. So to get back into that editing environment that we described before, you can just double click on the mechanism itself and it will reopen all of this. Now, if you remember in the last video, we made a point of defining the axial ranges and we gave ourselves two workpiece coordinate systems. We didn't bother renaming the second one though, so let's go back in and do that. And I've done it this way around just to highlight how easy it is to dive straight back in and make changes to things that you've already defined without having to worry about reinstantiating the whole thing. So I'm going to call this one BLT slot. Nothing to do with the sandwich, everything to do with it being the bottom left T slot though. And I'm quite happy with that, so I'm going to leave that as is. I'm also going to take a look at the simulation because I would quite like to make sure that the ranges of motion on this all pass a sanity check. So we can click on demo now. And so far, everything looks pretty happy there. That's exactly the kind of range of motion I was expecting, which is what we're after. You can also define the home position that you want your machine to have. Obviously, for the sake of actually being able to access this machine in the real world, it makes sense for the functional home position to be with the table right at the front, because who wants to be climbing inside a machine to check a vice is tight, you know? And finally, we are going to take a look at the style, which may seem a little extraneous, but with the machines that I use for my tutorial videos, I like them to have a fairly uniform color scheme. So if we click on style now, we can see that we've got the 3D model colors as imported. We also have classic and restrained options, which are ironically both a little bit jazzier than what we're going for. So we're going to click on gunmetal. I'm also going to switch back on visibility of the enclosure so we can see this here. And we can bump up the visibility a little bit if you want. It's, you know what, yeah, let's do so. Let's put it up to 10%. So we've got a little bit more than just the vaguest hint of its existence. Now I'm quite happy with that. So I'm going to click on apply. And that is now a done deal. The next thing that I'm going to show you guys is some of the finer details that you can define. Now, all of these will be defined by the details of your machine's controller, so you will really need to trawl the manuals for this, okay? So if we click on assembly settings now, you'll notice we get a whole bunch more options here. So we've got a lot of things that are generally down to the minutiae of the machine themselves. So in this case, for example, we've got the ability to deal with polar interpolation, which is typically something associated with 4-axis machines, so it's not super relevant right now. We've also got the assembly developer. Now, I don't know about you, but my name is not headquarters, and I'd be surprised if yours was. So I'm going to type in Jerry here. The origin list parameters I'm going to leave as default. The same with all of the 5-axis details here. We do not need to touch those for a 3-axis machine. We do, however, have in this particular controller the ability to define arcs in more than just the XY plane. We can do it in YZ and ZX as well. So let's click on those. And also, if I remember correctly, this controller can handle full circle arcs, so we don't need to break the circles. You've got the options for quadrants and halves as well for different controllers, because some controllers like to break them. Older controllers certainly did. If you happen to have a sufficiently old controller that doesn't support IJK or R functions properly and instead interpolates circles into a series of tiny steps, you can just turn off use arc as well. But that's generally for quite limited or very old school machines. You can, of course, also define the arc lengths and radiuses that are required for this sort of thing, but for this machine, these settings look right. So taking a look through the axes menu as well, you have got the option to define the workpiece connector priority as well as the linear axes priority as well. So that's basically the order in which it gets listed for the end user in ENCY. So X, Y, and Z is what we're expecting to see. Table center, then bottom left T slot. Yeah, that order works just fine for me. Clicking on each of these as well to open them up will give you some of the access that you had before, so it allows you to define whether or not your axis movement is continuous, indexed, or manual. It also allows you to define channels of control as well, which is typically more relevant to either multi-machine setups or to things like Swiss machines, which again, not super relevant right now. Tool change position. This is again entirely down to your particular machine and where the tool changer is, if you have one. You can also turn off simulate tool change if you don't really have time to watch it go back to the 0 point that you've set, but realistically, might as well leave it in there. It's an extra 2 seconds, you know. I'm not going to change these values because I don't have the tool change defined in this, and also since I'm not standing in front of the VF2 itself, I don't know exactly where its tool changer is. We move on now to a potentially very dangerous topic. Defining collision parameters is something that really should not be entered into lightly. It's very, very useful if, for example, you have a series of jigs that you remove that you want to include in your model, so you know where your actual machine part is relative to where they stand. Or if, for example, you want to stick within a hypothetical enclosure, but you don't want it to throw errors every time it gets close to it. But be very, very certain, because if you add a collision exclusion and it's not the right one, you are in danger of a very expensive mistake. So to show you how it's done, the way that one sets collision ignorance settings is you define your first node. So in this case, we are going to go with axis Z, and then the second one is going to be axis Y. And now what that means is, if there is the range of motion available, if we were to apply this, the Z-axis could functionally crash into the Y-axis without ENCY considering it a problem. Now, obviously, this isn't something that we want, so I'm not going to define that, but it is worth noting as a potential option, again, especially if you're dealing with multi-machine setups. So say, for example, you had a robot tending this mill, you would want to make sure that the robot arm didn't consider an intersection with a particular part of the enclosure to be dangerous. Okay, that of course is assuming you leave your enclosure doors open. In that sort of instance, you'd have whatever system set up, and that's on you. But I've shown you how to do it. I will tell you once again, be super, super careful with this, because bending a £100,000 machine is not anyone's idea of a good time. Back on to slightly safer topics, leads. So this defines the approach and return rules that you have at your disposal. By default, with 3-axis machines, approach being X, Y, then Z, and return being Z, then X, Y, it's a pretty sane standard. Obviously, these things get a little bit more confusing when you're dealing with things like 5-axis setups or even 4-axis setups in truth, and especially with robots. But for this, it's a pretty good default. Obviously, if you have other things set up on your workbench and you want to make absolutely sure that it moves away in a particular manner, you can define the details of that yourself in here. That's not a problem. And finally, we've got submachines where we can add things like a 4th axis, but realistically, again, we're not doing that in this particular instance. There will be further videos where we do much more detailed setups, but this is just to get you up and running on what is realistically one of the most common machine types out there. So I'm just going to make sure that those collision rules haven't saved, and they haven't. This is good. And I'm now going to click on Apply to close this menu. So we've now gone and defined ourselves a fully working 3-axis machine with enclosure and with the appropriate tool placement setting. I'm going to click on the Run Simulation button up here and just demo it once again so we can absolutely finally sanity check that we've done the right thing and that we're totally happy with it. That looks good to me. I hope it looks good to you as well, because I'm going to stick with it for now. So let's close that. And we are going to save the project as VF2 test. So we'll select that folder. And we're now going to export this into ENCY. So let's click on Export Scheme to ENCY. Presumably I had a different project open at that point. Just give it a second to think about what it's doing, and ENCY should have that model now. Nice. So if we zoom out, we can see we have got a rather snazzy looking brand new VF2 in here. Now, there is one final note that I'd like to go through. I promise I'll be quick, so I don't need too much more of your time. If you find yourself in a situation where you need to make changes to the machine schema, and you either can't open it up in MachineMaker, or you don't have access to MachineMaker due to IT policies, or you don't want to make it into a permanent change, which, again, I would advise we don't make permanent changes if we can avoid it, you can edit a lot of what we've just done using the Machine Setup tab here before you define any operations. So you've got things like machine state parameters, where you will automatically be able to adjust the min and the max values there, which again is super useful if you've got other jobs set up on your table and you don't want to have to break them down. So say for example you had something set up on the far left extents of the table, you can limit that -508 all the way down to about -300 or something like that, and still have a perfectly workable machine. This sort of update will only take effect and stick with the job that you are currently working on right now, so this project file and none other. Okay, it will reset back to norms every time you open a new project file with this machine definition. If you wish to define a modified definition that you're going to use for a run of jobs, but you don't want it to be a permanent change, you can define the change and then you can save a machine setup. Now to do so, you hover over the save icon here and you can save as machine setup, and you can open your machine setup each time and then start building your job in there. That will retain the changes that you've made, but it won't make permanent changes to the machine schema itself. Sounds like a bit of a roundabout way, but it's generally the most conservative in terms of dealing with permanent changes, because we don't want to find ourselves making a series of permanent changes that the next user doesn't know about, and they start programming the machine as per usual and find that bad things have happened. Okay, so it's worth noting that this is possible, and by default it will reset back to norms every single time. Beyond that, I hope this has been useful and informative, and as always, happy machining. See you in the next series.